Hello everyone. Thanks to everyone for watching this video. My name is Qidang. I'm an amateur musician. Today's video is titled Harmonic Series, and it is going to provide you the application of fast Fourier transform to global notation. I am going to give you an overview of what I am covering in today's video. First at all, it is an introduction of harmonic series, and then focus on the fast Fourier transform and global notation before wrapping up with conclusions. So far, as example, the simple motion of a moving string. It can be a guitar string, a violin, or piano, excited into movement by plucking, striking, or bowing it. It makes no difference, because the acoustic laws I demonstrate through an example are the same for all instruments, no matter their type or principles. In this video, I will show how the laws that apply to string instruments. For now, let's listen to music and take a look at violin strings. Why does the violin or guitar string move like that, and not how one would imagine? And why is this sound considered musical? The answer to both questions is harmonics. Harmonics are different ways of movement, happening at the same time. The first type of movement is the simple motion that up and down like a jump rope over the entire length of the string. The second type of movement divides the string into identical but opposite parts, each oscillating like the first harmonic. The third simple motion divides the string in 3 equal parts. I'll stop at 3 for now. The summing implies the simple addition of every point along the lines. If all shapes are above the dotted, neutral line, they add up. If we extend to the 4th, 5th, 6th, and so on, harmonics increase the number of vibrations, creating every time a new tone, which is nothing but a reiteration of the fundamental every time on an even higher level. The intensity of the harmonics is given in the table as exponents, ratios, and percentages. The resulting numbers are the same. Both numbers are all 1. Notice the connection between the frequency of harmonics and the inverse power of 2. This is a connection between mathematics and music. Now we will introduce the Fourier series to detail the idea of the decomposition of a music signal into sinusoidal components. If we have taken calculus before, we are probably familiar with the Fourier series, which takes any periodic function in time and decomposes it into the sum of a constant, and then a series of sines and cosines are defined by their frequency. We are summing over each individual frequency of sine and cosine. Let's look at this music signal as an example. This signal is represented in what is called the time domain, because each point on its plot represents amplitude as a function of time. This is what your eardrum actually vibrates when you are listening to music. But despite it being so messy in the amplitude, if we instead decide to translate it to the frequency using a Fourier series, we get waveforms of frequency. The reason is that each frequency from 20 Hz to 20,000 Hz is equally represented in a music signal. The signal is composed of a sum of all the cosines and sines of all different frequencies. The next question then is, how do we calculate those coefficients at each particular frequency? The answer is to use a Fourier transform. If we are familiar with calculating correlations, the Fourier transform is essentially the same thing. We are multiplying a function. Now we can represent the sinusoidal function as a complex exponential. But if we are afraid of complex notation, this representation actually makes the integral much easier to use. The result is you get one complex coefficient for frequency. If we insist on working in real notation, we have to calculate two different integrals, one to correlate the signal with a cosine function, and one to correlate the signal with a sine function. We get two real coefficients for frequency. The most people find that working with one complex coefficient and completing just one integral makes things a lot easier. The integral is from negative infinity to infinity. You don't need to do this in practice, because we are always collecting data on a signal within a finite time frame. An analog to digital converter also cannot sample continuously. So, it is a set of discrete points running from time equals 0 to the nth sample that we were able to take, in order to conduct a Fourier transform on a discrete set of samples. The discrete Fourier transform DFT is only slightly different with the continuous Fourier transform. However, the computational cost of the DFT is very expensive. We need a fast method. Fortunately, the fast Fourier transform FFT is a quick, smart way to do the DFT. We can first divide up the DFT into an even index summation and an odd index summation where the subscript. So the even index is 2m. For the odd index sample, it is 2m plus 1. So now, we have a DFT as the sum of two smaller summations, each half the size of the original. Let's move the 2 in the numerator to the denominator for both the even and the odd index. And we can simplify the odd index term by distributing out a constant, which we can move to the front of the summation. Now we notice that the exponential terms in both the even and the odd index summations look identical. There is something tricky about this particular exponential. If we expand using Euler's formula into cosine and sine terms, we will know that k runs from 0 to n, which is the total number of samples that we take a look at what happens when the value of k is larger than n over 2. If we define r as r equals to k minus n over 2, and r runs from 1 to n over 2, we can distribute the numerator and divide out the n over 2. We can find that there is a negative 2 pi term in the operand of the cosine. Now, every time that we add a multiple of 2 pi to the operand of cosine, we end up with simply the cosine function without the 2 pi multiple. So, our k value is larger than n over 2. It's simply a repeat of the k value minus of n over 2. This is what is called the symmetry identity. As a result, the exponential terms, because k runs from 0 to n, everything repeats after k equals n over 2. We can repeat this process and then divide each of these summations into their own summations. Every time we split the summation, and we are having the number of operations to calculate the DFT. Now we know the details of the FFT. Next, we will explain how to use the FFT to analyze the music frequencies. We can listen to a piece of canon in D. Then we can collect the music data into the FFT and get a waveform and pitch time graph. In this case, the waveform graph shows the extended blocks of sound characteristic of sustainable sound sources, as each block tends to begin where there is a new syllable in the text. The waveform graph might help when it comes to specifying articulation, but it doesn't tell us anything about pitch. The apparent from the pitch time graph is that while there are slides and fluctuations of pitch, there are also substantially flat segments where the music remains on a stable pitch. Moreover, some of these stable pitches recur several times in the course of the phrase. That, of course, is the definition of scale degrees. We will do this in the usual way, by drawing a horizontal pitch line for each scale degree. The procedure is to draw a pitch line into the graph at each height where we see more than one horizontal segment in the melody line. The hurdle means 4 beats per bar, each divided into 2 pulses, at a tempo of 126 beats per minute. The intervals between each scale degree and the reference pitch can be obtained by the equation of 1200 times log2 B over A. In the 12-tone system, we can use this equation to know the cents at each interval. Semitone is 100 cents and tone is 200 cents. In our case, the intervals are tone, tone, semitone, tone, tone. Finally, we can listen to the piece of Canon in D again and look at the notation to understand how the music plays. From conclusions, what we learned: modern tuning system can be used to solve problems of modulation and consistency caused by the pure ratio intervals that our ears want to hear. Fourier analysis is useful in modeling and breaking up sound, and the Fourier transform opens up practical possibilities to model and define sound using Fourier analysis. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.